Hi, everybody. Welcome to Orgoland Reactions. Woohoo! But before I get into this little video, I have to let you know this is the fourth attempt at this video because in all the other something's happened. Wi-Fi disconnects, speakers don't work. Something has happened to try to make this video. So if I survive and if you see this video, it will be a miracle because it just hasn't seemed to want to happen. Okay. Whew. I love Orgoland Reactions. So it's very good that we have to do this video over and over for me because I love the fact that we're getting into this part. This is the main focus of really all the rest of organic chemistry is how do you make different functional groups? All those functional groups up there. How do you go from one to another? And so we're going to start investigating that. And that's what the rest of the summer is going to be about, is really how do you take one molecule with one functional group and turn it into another functional group. This is the part in Orgoland where students think that if they write all the reactions on flashcards and memorize them all, they will be perfectly fine. But that would be like me telling you to memorize all the sentences in the English language, and so that you knew every sentence in the English language and would be able to, you know, scroll through and spit out to me the proper sentences that you need. That doesn't make sense. So as a language, what we're going to do is show you what I'm going to do is show you how the framework for this language works so that you can use this framework and apply it to any reaction you see. And I mentioned this very early. Oh, let's see if this works. I have doubt now about everything. But everything you need to know about Orgoland is plus loves minus. This is the first time you'll actually get to see that in real life, in real time. Cool. There is a biological application, as always, so I love to throw these little biological tweaks in you. And just to let you know, my adrenal gland was kicking out adrenaline a minute ago because, oh my God, I couldn't believe that for the third time in a row, this actual video crashed. So my adrenal gland pumped out some adrenaline to help me get through this chaos. What was going on? My brain sent a signal to create the adrenaline from norepinephrine. And so to do that, to take norepinephrine and create epinephrine, adrenaline essentially, my body had to do a nucleophilic substitution reaction. It had to take this amine, react it with the methyl. The methyl had to lose a bond to the sulfur so that I could have the methyl on my norepinephrine, and that would change it into epinephrine. Chemical nucleophilic substitution organic reaction happening in my body right now. Okay, so lots of other ones like this taking place in our body because we are organic beings, and this is just one of many, so I thought I'd show it to you. So let's get clear then, that was a very specific nucleophilic substitution reaction. Let's make sure we're clear about all nucleophilic substitution reactions and how you would spy one. How do you know you're looking at a nucleophilic substitution reaction versus, say, a acid-base reaction or a redox reaction? So how are you going to know? So the first thing you are going to need is a nucleophile. A positive loving species. So these are very easy to spy. Usually they have to have a partial negative charge. If you're going to love plus, you better be a little minus. And so if you're a little minus, oftentimes you have a lone pair. And it's that lone pair of electrons that is searching out, looking for a positive charge to react with. And so it is a positive loving nucleophile. Okay? Notice it doesn't have to be negatively charged, but oftentimes our nucleophiles are negatively charged, which makes them even more positive loving. So keep an eye out for your nucleophiles. But in a substitution reaction, it's got to substitute for somebody, and that nucleophile has to fall in love with somebody. So to get a better sense of this, let's look at a real life reaction versus this totally, you know, generic one up here. This is 2-chlorobutane reacting with hydroxide, which could have come from, say, like potassium hydroxide or sodium hydroxide. But those spectator ions I just don't pay attention to, because all I want is my nucleophile. I want the hydroxide. And then it's swimming in some water. And this reaction is showing you how to go from an alkyl halide to an alcohol. So even though we're going to dive into the details of nucleophilic substitution, please don't forget, you're doing a functional group transformation here. You're going from an alkyl halide to an alcohol. Very cool. Maybe this is happening in your body too. Who knows? All right. So let's make sure we can spy this kind of nucleophilic substitution, any nucleophilic substitution, because they all need 4 things. 4 things. Yes, of course, they need a nucleophile. So you got to spy this nucleophile, right? But the nucleophile then needs to fall in love with, you guessed it, an electrophile. More specifically, an electrophilic atom. Now, granted, the substrate usually refers to the whole molecule that has the electrophilic carbon or species on it, but this nucleophile is looking for an atom that is an electrophile or electron-looking loving species. And that's what this blue carbon is, because the chloride is sucking electron density away from it, and therefore the chloride is going to have to and want to and can't wait to leave. So it's great. We call this group attached to the electrophilic carbon, we call it, and it has to have a leaving group. So something that will fall off, take a pair of electrons and fall off, and be happy all by itself as Cl-, for example. So this is really a soap opera. We got love happening here. We got these two. The OH- is trying to fall in love with the blue carbon, but the blue carbon already has 4 bonds. Wait, Cl- is trying to take the money and run. Yes, it got a divorce when the OH- came on, and oh my God, what a soap opera this life of Orgoland is. So not a bad idea to keep it in that kind of frame of mind. What's the 4th thing? Well, there's got to be a scene where all this soap opera action is taking place. A room, a hotel, somewhere, a house. So the house, the room, all has to be in some solvent. So it all has to be swimming in some container and swimming around with a bunch of solvent molecules. And you'll always recognize the solvent for a reaction because it's written above or below the arrow in the reaction, okay? Not as a reactant usually, because it's not a reacting species. It's just what everybody wants to swim in, okay? So those are the 4 parts. If you can spy all 4 of those parts, you will be well on your way to figuring out the products of any nucleophilic substitution reaction, because you'll have classified them as such and can go from there. What? Oh my God, what are rate laws doing in Orgoland? I thought rate laws were an intro chem. Ah! Okay, the adrenaline's kicking in now, right? Right? You have the little adrenaline now, it's your turn. So, yes, because there are different mechanisms that take place for different nucleophilic substitution reactions, and the names that are given to these 2 different processes relate to their rate laws. So let me show you how the rate laws developed and why they are different. And remember, a rate law is telling you what's taking place in the slowest step, the slow step of the reaction mechanism for how it's taking place. And therefore, that step is what we want to pay attention to if we want to make our reactions go faster and better or slower and worse. So let's take a peek at these 2 reactions that are very, very similar. Experiment 1 is done in water. Experiment 2 is done in this solvent known as DMF. This is an acronym for dimethylformide, which we'll see in a little bit. So very subtle difference, and that's the way I want to start. I want to see if I just tweak the 4th littlest thing involved, could I get 2 different rate laws? that means that little tweak caused drastic differences in the way these two reactions work. So let's play. So this is rate law information. You might remember it, might fire a neuron back there somewhere. Boom. Yes, hopefully it didn't scare you, sorry. But it's really cool because it'll help and let me know, does the substrate leaving group piece of the molecule, our 2-chloropropane, have an effect on the rate law? And does our nucleophile have an effect on the rate law during the slowest step of this entire process? It doesn't mean that, you know, I still need both of these things to have a nucleophilic substitution, but do I need both of them in the rate law? Take a peek. Double that concentration, look at the rate. Notice how the rate doubled. So, yes, 2-chloropropane matters. If I increase its concentration, it will make the reaction go faster. Okay, great. So we do the same thing with our nucleophile, our OH-. We double its concentration while keeping the substrate leaving group constant. And we look at its rate. Wait a second. Nothing happened. The rate didn't increase at all when I doubled the nucleophile. This is really weird. I have a nucleophilic substitution reaction where evidently in the slowest step of this reaction, the one that matters the most, it doesn't matter what the nucleophile is at all. It's not helping me increase the rate of the reaction at all. That's really kind of weird. Okay, so let's see if experiment 2 is the same. Then we got some weirdness going on. Doubled its concentration again of substrate. Notice, same story, it doubled. So again, 2-chloropropane does matter. Good thing. I want something to be constant and matter here. But now what's really kind of cool is you notice if you double the rate of the nucleophile, woo, now the nucleophile matters. It actually is first order with each substance in the slowest step. And so what this means is these two experiments, even though they're both nucleophilic substitution experiments, they are both taking place in completely different ways. That the slowest step involves something that's happening that's completely different than what's happening mechanistically in the slow step of the second experiment. So let's go play. Let's go check out what's going on here. Let's make sure we check it out with the appropriate names so that we speak orgo to each other and now know what we're talking about between these two experiments, and we'll give them names that'll classify them for us, allow us to talk about it in secret code, and nobody will know what else we're talking about. So in that first experiment, there was only one species in the rate law. So we're going to call that one nucleophilic substitution 1, or SN1. One species only in the rate law. As you can see, perfect name for the one that involves both the substrate and the nucleophile are involved in the slow step. You need both molecules too. We'll call it SN2. Sounds simple enough, but please remember this, that these names are associated with their rate laws and not necessarily the other things we're going to see in a second with how they actually work, how they actually form products. It gets a little confusing, I warn you. So come back to these and hold on tight so that we're calling everything the right name, SN1 versus SN2. Okay, let's play and look at SN2 right now. And then we'll go look at that weird thing, SN1, that didn't use the nucleophile at all in the rate law. Like it didn't matter. That's kind of weird. Let's hold weird off a little bit. Let's dive into SN2. So SN2, this is the reaction that you see on paper here. The reaction is just showing the reactants and the products. Great. If I ever ask you for a reaction, this is all I'd expect you to put on paper. But if I ask you to show me the reaction mechanism, Mechanism is how things actually work, how bonds form, how bonds break. So the reaction mechanism for SN2, our slow step that requires both molecules, occurs like this. And again, we use these arrows to show the movement of electrons. So this is what takes place. The reaction happens, and I produce this product. Now, this is all very nice and beautiful, but you know what? I found even something more beautiful to show you. That really, if you could get this mechanism explained to you from someone in London, with a British accent, okay, there's something about, maybe it's the fact that my wife in the pandemic has been watching nothing but Downton Abbey, and so British accents have been ringing throughout our house all over the place. But chemistry with a British accent. Check this out.
Primary halogenoalkanes undergo SN2 reactions, where the S denotes a substitution reaction, the N shows the reaction involves a nucleophile, 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. The transition state complex.
So if that just doesn't do it for you, I don't know what. I mean, I'm sorry. That's a beautiful little video animation of this backside attack and the umbrella unfolding and all the things that you see here. And notice that might have a stereochemical influence on the actual molecules we're playing with, since it has moving bonds in different space. So the way to show it in that reaction mechanism is, notice I used arrows to show the formation of bonds and the breaking of bonds. So this little slide is a little commercial break that just makes sure we're clear about these arrows. You've been using them before in resonance structures, so this shouldn't be something completely new. I've been trying to build it in throughout the entire summer. But Professor Julia Miwa created these 10 commandments of mechanism drawing because they're so finicky and picky and specific. Then I've only put 3 of the 10 commandments. If you want to know all 10, please let me know and I'll send it out to you. But a mechanism is really, really important to show to the reader exactly how the bonds form and how the bonds break. So to create this new bond in the product between the nitrile and the CH2 that's over here, I need to show the pair of electrons in that nitrile reacting with that electrophilic carbon. And what I don't want you guys to do is to do something like this, where you just kind of point at it. Yeah, it kind of goes over there. And it kind of goes over there and kind of just lands somewhere on one of those carbons. Oof, please don't do this arrow. it's not helpful. It's not telling me exactly where that pair of electrons is going. So please use an arrow that shows exactly which atom that lone pair is trying to attack and bond to and fall in love with. Okay, and then you'll notice in this mechanism, there's no way I can make that bond without breaking a bond. So arrows always start at the pair of electrons, whether they're in a bond or on a lone pair. I can never move positive charge. Remember, positive charge means there's nothing there. It's empty, an empty p orbital. And how can you show an arrow moving emptiness? Moving empty? Don't move positive charges. Always move lone pairs and bonds. These are things with negatives in them, all the electron density. Move negatives around to show how something gets electrons and steals the electrons from somebody to become less positive, making whatever they stole them from become more positive. So that's the key to mechanism drawing. Okay, and the outcome here, so we're not going to show this one. This one's happy days. And there's another little new notation here. It looks like this is cyclopropane. This is not cyclopropane, not where it's positioned on the arrow. We would never use cyclopropane as a solvent because it's gaseous at room temperature. So what this little triangle means in the future, please try to keep in mind, this is our notation, so I don't have to write out the word heat. This reaction got heated. So if I want you to heat a reaction, I just put a little delta symbol, a little triangle here, and it lets you know that the reaction's heated. Okay, cool. The homework this week has lots of mechanisms for you to practice with. They're on reactions that you may have never even seen, because what I want you to do is just look at the product, spy from the reactant what new bond has been formed, and then try to show me from the reactants which pair of electrons were used to create that new bond. So it is a little detective game, mystery, what's new, how did it get there? This is what mechanism drawing is all about. And by pushing this pair of electrons and joining with this carbon, this oxygen now takes on a formal charge of +1. And granted, there probably is another step in this mechanism because oxygen hates being positive, where some other atom loses electrons to the oxygen and goes away as a positive charge. Okay? But mechanism drawing is like resonance drawing structures. It's very methodical, very slow, very detailed. Please do not skip any steps. Otherwise, there wouldn't be 10 Commandments by Professor Julia Miwa. Okay. So, all right, enough of this commercial break. Let's get back to the business at hand, SN2 reactions. So what I want you to see in this summary slide is that I no longer have 2-chloropropane, I have 2-chlorobutane, which means this is a chiral carbon, because I wanted to emphasize this idea that stereochemistry might matter. And so to practice stereochemistry, please try to figure out if this is an R or S enantiomer for 2-chlorobutane. And then notice this chloride is the #1 priority in our 3 dead chemist rules of determining RNS. And notice the Cl is what's falling off. So when the #1 priority is the group falling off, and the #1 priority on the product is the new species coming on, then in this umbrella inversion process, inversion process of a backside attack, when we invert the umbrella, it is possible that maybe you invert the stereochemistry. So check and look and see if this product, this alcohol, what is its chiral form? Is it RS? And what happened from beginning to end when you do nucleophilic SN2 reactions that require a backside attack, like the British person said, and I will never try to impersonate a British accent, as my wife has already told me. I am horrible at it, so I won't hurt your ears with that. But as the cool British movie talked about, when you invert the umbrella through this transition state, you could invert the stereochemistry. So let's play and practice and come to class with a possible answer to cut and paste into your Jamboard for the answer to this question, which again, keeps bringing back nomenclature, keeps bringing back stereochemistry, and even things like potassium hydroxide, I want you to realize is going to disassociate and fall apart. And here is our old friend DMF as the solvent. So do not treat DMF as a reactant. It's not a reactant. It is always used as a solvent. Okay? All right, I hope these questions were fun, interesting. I hope you feel like you're gonna get in there and start making things. And this is a little bit about SN2. And now that we know kind of what are the properties of an SN2, we're gonna start looking into what makes a good nucleophile, what about the electrophile, what kind of good electrophile can I have? What are leaving groups? What kind of leaving groups are out there? And then of course at the end, we'll talk a little bit about solvent like DMF and what's the role the solvent played. Why did the solvent change experiment 1 to experiment 2 and create 2 different rate laws? Solvent has a role somewhere. All right, here we go. This is really cool. Okay, I hope this video worked. This is my 4th time doing it. Woohoo! See you soon. Bye.